So today I'm here with my good friend Ty Branneman, and we're going to be answering some of the questions that came in on both of our YouTube videos and also in the podcast section over at our website. So we're going to go ahead and get started. So thanks for coming in.
I'm glad to be here. This is fun. Thank you.
Yeah. So we're going to start off, and a technician by the name of Leon had asked, none of the units I have or work on have the info for subcooling. So how do I determine the subcooling on these units?
Well, the first question would be, what metering device do you have?
Yes.
So if you have a TXV, the unit will, a lot of times it'll be even in the installation manual. So you have to go back to that book, that guide. And I've also noticed that some of the units will have a specification, how long is that line set? Even if it has it on the tag of the unit and it says, say, 10 degrees of subcooling for a TXV, it says, hey, if your line set is over 20 feet, they want you to add a certain amount of subcooling. So even in that installation manual, it's not fun to dig through that installation manual, but a lot of times I've found that information in there, and it's not easy to find all the time, but it's in there. Now, if I have nothing to go on, I have a TXV, there's nothing to go on, there's nothing inside there at all, you can use some rules of thumb, but there's only when all else fails to get you by, we can use some rules of thumb, and typically I like to see 10 or 12. But I really can't stress enough, go to that manual first. And if you don't have the manual, you can look it up. Use part of the model number and do a search for a PDF, and you'll be surprised at how much information you can get off that system.
Great. Yeah, a lot of rating plates are worn off. You can't see them, or they're scratched off, or they just don't have them posted on it. Sometimes you can take the shroud off and it's on the backside. It might have more than one target subcooling depending on the outdoor temperature. So yeah, you're going to want to use the manufacturer's literature in order to set that subcooling correctly, and only on units that have a thermostatic expansion valve as the metering device. And if it has a piston, then we need to check it with the total superheat method. So
that's
great.
Correct. Yes.
So a technician by the name of Manny asks, greetings. When you have a liquid line restriction, what's the difference between putting the TXV bulb in hot water or cold water to see if that happens to be the problem?
That's just a great way to see if that TXV is actually responding. The bulb's not going to tell you what it should be or anything. You're just looking to see if it is responding. So when I put it in hot water, I want to see that that bulb is sensing that we have a very warm line. So the TXV is going to think that our superheat's going up, and it's going to try to open to let more refrigerant through. So I just want to see that there's going to be a change, really, with pretty much anything. I'm really looking at superheat to see if it's going to change. Put it in cold water and it should change back in the opposite direction. We can go into all the details of what it's doing inside, which I really love, but ultimately we're just looking for a change. Another thing is, if you're looking for a restriction, I like to be able to see what the subcooling is before that metering device. In a perfect world, I would install a service port before that metering device so we could actually physically check the pressure and the line temperature to get a true subcooling before that TXV. But if you want to see if that TXV is responding, it's a great way of using that sensing bulb and temperature change.
So that would be for maybe two reasons, right? When you have a filter dryer before the metering device, that would be one reason. Another reason would be due to a pressure differential because a long line set or a height, like some type of a line set extreme height difference or something like that, that could cause a pressure drop, which could affect the subcooling coming before the metering device. And so you want to have at least some subcooling before the refrigerant hits the inlet of the metering device. That's great. And when we are putting the bulb in hot water, the superheat should be less because it's allowing more refrigerant into that indoor evaporator coil. And then when we put it in cold water, the superheat should increase because it's not allowing as much refrigerant across the coil. So those are some things that you could do. And if it's not responding at all, that could be maybe the bulb has leaked all the refrigerant out, right?
That's
so
correct.
We have, can you speak on the TXV bulb changes over time, or like TXV design changes up on that head?
Oh, yeah, they do change, especially with different refrigerants. So I've seen people before convert a refrigerant system to a different refrigerant, and that TXV, that head, and the spring retention inside is specific for the refrigerant it's working with. So definitely want to check with those properties. But some of the refrigeration systems we have, you can actually change just the head out, the power head. So and that's nice, and you can use cross references where it has the same refrigerant or even a different refrigerant that's in there. And there's a lot more. There's a whole entire science that goes into how that TXV works. One of the things that we really got to consider is making sure we're getting enough liquid refrigerant to that metering device. And the old days, we used to put a sight glass on there, not for charging, but to see that you still have that liquid and to see if there's any contaminants. But one of the things a lot of technicians overlook is making sure that we have liquid to that metering device.
Yeah.
For example, if that liquid line runs up into the attic and the attic is a lot hotter than the temperature outside, you're actually losing subcooling. You can have 10 degrees of subcooling outside. Before it actually gets that metering device running across a hot attic, you could be at 0 degrees of subcooling, which means you're not feeding a metering device enough refrigerant, and you have that issue. So having a service port there, or having a sight glass there to know that we're at least getting enough refrigerant to that TXV is good. And a lot of people misdiagnose TXVs. They have a clogged up filter dryer, or a kink in a line, or even running through a hot attic, and they see that, hey, this TXV is not keeping my superheat good. Well, it can't. You got to pay them enough subcooling. Pay that TXV enough subcooling, and it will do its job of controlling superheat.
That's great points. And so you're talking about with the refrigeration, TXV heads, the ones that would unscrew, and you could replace them with a different head with a different refrigerant potentially, and then that you could adjust that and set the superheat properly. But with the comfort cooling or air conditioning ones, a lot of times they're just brazed in place, and so a lot of times we just have to replace the TXV if it is bad. And a lot of times the TXVs get a bad name because of what they used to be. And a lot of them used to be a non-galvanized, just steel head that would rust and leak refrigerant, like over at the head or the tube. And now they have all those stainless steel heads on them, and they don't really leak that often, So it's all of those things. And oils, it plays a big part in it too.
So TXVs are misdiagnosed for several reasons. One, we don't get enough refrigerant to that TXV. The second big reason I see is because there's not enough airflow. People think that it can help with airflow, but if you have bad airflow, the TXV can't do its job. And then a lot of technicians look at suction pressure. That TXV's job is not to control suction pressure. It's to control superheat. Right. So your suction pressure could still be too low because of airflow or because of the refrigerant not getting there. And it's still the TXV's doing its job. So understanding that it's trying to control superheat. And another one is making sure we have the lines clean. When we're brazing, making sure that we have that flow of nitrogen. I hear a lot of people say, oh, I don't need to flow nitrogen. And I have those same people will say, TXVs fail a lot. And I've never had a problem with that. Well, if you're changing TXVs, there's probably a reason. And, you talked about some of the problems in the older days. There was a compressor manufacturer that put an anti-rust or a rust inhibitor into the oils, and they had 3 different types that they used, and they chose to go with just one. And then with POE oil, it actually turned to a type of gum that would really gum up. This is in the early 2000s, and that caused a lot of TXVs to fail. Now, it wasn't the TXV's fault. It was, excess to it. And that was, I think, the moment that people thought TXVs were bad because of this oil and never really connecting it together. Yeah. It was a huge deal back in the day, and lots of TXVs were replaced. And unfortunately, that's why people started going with fixed orifices, because the fixed orifice didn't fail, although it caused other problems that people don't see. But yeah, the TXVs are just misdiagnosed, and then they got a bad name because of that oil side. And they're really, if we install them correctly, they do us so much better of a job controlling how that system's working, not just for efficiency, but for operation, performance.
Yeah, absolutely. You bring up a lot of great points, and I think we could talk about TXVs for a very long time. And you don't want to be adjusting them up front. That would be like the very last thing you would ever do. They always come factory set for, at least for air conditioning systems. For refrigeration, it's, you have to, maybe you might have to adjust them, but in air conditioning, you would never really adjust them. That would be a very last thing that you would do after doing all your other checks, and you're checking your subcooling, you're checking your superheat, you're making sure. So if the system has a TXV, you're checking the refrigerant charge with subcooling, but you're checking superheat to make sure that the TXV is doing its job properly. Yeah, and like you said, it doesn't hold that saturated temperature steady. It's checking the superheat and adjusting. It's adjusting for that, based on the indoor heat load. But I'm going to move on to an. Oh, go ahead. Oh. Yes.
A lot of the Goodman equipment now is sending out with adjustable TXVs, which I think is great because I like to be able to fine tune it. But they do specify to have subcooling first. It's like mentioned 8 times before you get to the superheat adjustment. Yeah. And it also says it needs to be running for 24 hours before you even try to adjust superheat. And it also says airflow first. So it goes through all these things. Hey, do all this first. Now, if all this still isn't right, we can adjust that TXV. But like I said, all these other things are so much more important before we actually get to that TXV as being the issue or adjusting it.
Yeah. Good guy. Awesome. All right, so we have a technician by the name of Ronald. He asks, what's the purpose of doing a nitrogen pressure test and also a vacuum test? Isn't just doing a vacuum test sufficient?
Well, that's a great question. And we hear this a lot. So I'm glad you asked, because we want to make sure that we cover that. When we do a pressure test, we're using just nitrogen and we're putting in a high pressure. And if we have a small leak in that system, it's possible for some type of contamination in a vacuum test to be pulled over that hole, and it will actually prevent it from leaking under a vacuum. But under a pressure test, it's actually pushing out the opposite direction. So pressure testing with nitrogen, we know it, nitrogen and time, the gas laws, that we can see that, hey, this thing is not leaking over a certain amount of time. And we can see that, hey, with temperature and the time compensation, we're not leaking. Now, we want to do that step before we pull the vacuum. So if I'm pulling a vacuum, I can know with the pressure test if I'm holding a leak or not. But if I know that I have a leak beforehand, I don't want to use the vacuum, because now I'm going to be pulling moisture into that system and pulling contaminants. And remember, moisture is a killer of refrigeration systems. So if I do a pressure test first, I know I'm not having any leaks. I know I'm not getting moisture in that system. And then I can pull my decay test. Now, when I do that decay test, I'm not looking for a leak. I'm really looking to make sure I'm boiling all the moisture out. So when I valve it off and I wait to see that it's not rising, I know that as a second check, it's a backup check for leaks, but also I know if it doesn't rise above 1,000 microns, that, hey, we also got the moisture out. If it's rising nonstop, then, hey, we failed. We have a leak somewhere. Let's recheck it. So it's nice as a backup, but primarily I want to use that nitrogen in there.
Yeah. I think a lot of wasted time occurs when people are trying to take a shortcut, such as just pulling a vacuum instead of doing the pressure test first. And like you said, you're pulling air into the system. A lot of times it's humid air. You're changing out a system a lot of times in the middle of summer when it's hot and humid, and you're pulling all that humid air into the system during a vacuum if you have a leak. But another thing is that it's the technicians waste a lot of time. And so you're questioning, well, where's my leak coming from? Am I doing this, doing that? They're looking at all their hoses, if they're pulling through a manifold gauge set, and it's just a lot of wasted time. And yeah, just do the pressure test, man. Just do that. It's gonna provide inert, dry nitrogen into the system, and then you can purge that out. You could also be doing what's called a triple evacuation and flowing nitrogen through it in between your vacuums, but you don't even need to do that. You can just do a single vacuum if your decay test is steady. The decay test is for when you are shutting the vacuum pump off from the system and you have the vacuum gauge close to the system, and you are just measuring the true vacuum level in the system with the vacuum pump off, instead of measuring the micron level while the vacuum pump is running, because that is going to be lower than the decay test number when you shut the vacuum pump off.
And when you first start that system up, that's the most important time. You can't go back later and do that pure nitrogen test. You can't go back later and get that pure vacuum you do. So you have the choice as a technician. There's no HVAC police. You can cut these corners and not pull a proper vacuum and not pressure test, but really somebody's paying for that. And it's usually going to be the customer and the longevity of that equipment. So you'll see somebody that does that and they get away with it. And hey, there's no HVAC police. I've cut corners before. Unfortunately, you have to get through some jobs. We make excuses, but ultimately the customer's going to end up paying for that. So if we spend the time of doing that nitrogen test, we know we're saving the time of knowing right up front. So it's a direct save there, and it's a save for the customer. Then we do the vacuum test. We get the vacuum down quick. It's down low. We know there's not going to be moisture, which means there's not going to be acid, which means there's not going to be copper plating. The compressor lasts longer. There's less leaks in the system. I think everybody wins. So some of these small steps that we do, they're really that longer, for the customer. So sometimes you're in a hurry and you got to stop and think, hey, if I cut this corner, there's going to be consequences. Am I prepared to accept those consequences?
Yeah, the problem's like when even a technician wants to do all the right things, right? But they run out of nitrogen because they're on service calls all day. And that's one of your points right there. It's like, man, you really have to plan ahead with your service calls and things and your day. But the problem is, a lot of times the the service technician is getting their schedule. They're not in control of their schedule, essentially. And so it's hard to plan sometimes. And so that's just hard. So you just want to have all the right tools in the truck just to be safe and be ready.
Best practices. We're not saying, hey, you have to do this every single time, but it's so much better when we do.
A technician by the name of Jerry is asking, in the manual for a mini split, it says to run the vacuum for 25 minutes. I don't understand why. That's a shame. That is one of those manuals. I've seen a lot of manufacturer manuals that are just, say, reprinting things that they've used in the past. And so our practices are way better than that. So it doesn't matter as far as time. You could pull a vacuum down to say 200 microns in 3, 4, 5 minutes. Even 1 minute, it's possible to pull that down. So you don't have to pull it as long as 25 minutes. Likewise, it's all about hitting the micron level of 500 microns or lower, and that's stated by the EPA 608. But a lot of times we want to pull down to a deeper level. And what that means is we are dehydrating the system. We're pulling any air, nitrogen out of the system. We're pulling the water vapor out of the system to prepare the tubing for refrigerant. So time doesn't matter. It could be a 50-minute vacuum. It could be a 5-minute vacuum, as long as we pull down to below 500 microns. And then we valve off the vacuum pump during the decay test or the standing vacuum test, whatever you want to call it. And we watch our vacuum gauge, our micron gauge. We want to make sure that our microns do not continue to rise and that they are holding steady below 500 microns. If you pull down to 200 microns and you have the vacuum gauge very close to the service ports, you're reading a pretty accurate vacuum inside the system. So it may only rise 100 microns or 50 microns or something like that. So we just want to make sure that it doesn't rise. Time is just not that important.
Yeah, that's one of the things. I've seen that in a few manufacturers, and it's like, I always say RTFM, read the fabulous manual, but sometimes, and that's I think the one case that I'm like, no, we need to do better. We got to do better. And I don't know how that slipped by for so long, but I'm seeing a lot of manufacturers now, they're wanting 200 microns. They're wanting it pulled down a whole lot deeper. And there's a lot of articles about that dehydration, but I agree with you 100% on that.
So this is not a question that's asked by somebody else, but I want to get your take on it. When the manual says you must do a triple evacuation and they want the final number to be at 200 microns, what's your thought on that?
So that's a great point. There's a few different viewpoints in this. So our goal is make sure we have that system dehydrated. That's our goal. We want to get that moisture out because it's going to turn to acid, which is going to kill our system. So we want to make sure our ultimate goals we're down to 200 microns. Now, in most of the places that I've lived, I can do that in one single shot. I pull a vacuum down, and with the decay test, key being that decay test, valving it off, and those microns don't rise up above 500 or 1,000, and I know that I'm dehydrated. I know that that moisture's out, and that's our ultimate goal. Now, if I do the triple evacuation, where I'm pulling a vacuum down and use nitrogen, it's not going to hurt anything. It's just taking extra time, but we still have the same goal. Now, some other scenarios, I'm working on, say, a chiller where I have water or potential water leaks in those lines. And if there's actual physical water in there, there's enough volumes that water could potentially freeze. Or if I'm up north somewhere or in the winter pulling a vacuum and it's below freezing outside and I'm trying to dehydrate that system, it is possible for the moisture vapor to freeze in there. So by using the nitrogen, and it helps push or flush that back out. But ultimately, our goal is to be dehydrated. And most of the time, we can do that without a triple evacuation. But if you're in doubt, hey, do the triple evacuation. You know, it's okay. Now, when you get into more little details of it, you get to see the science behind it. There's a book called Vacuum for the Service Engineer that goes into all the details and every possible scenario you could ever imagine of when you would need to do that and when you wouldn't. But our ultimate goal is, hey, we want to make sure that system's dry. And if we're flowing nitrogen while we're working, we're really pushing the majority of that moisture out anyways, which is the whole idea behind the triple nitrogen evacuation. But if a manufacturer says to do that, hey, you know, I think I can do it in one shot, but if the manufacturer wants that, it's just a little extra time.
Mm-hmm. Yeah. Yeah. So great points. One thing I notice is in some manuals, it might be for mini split systems that only have one port. And so when you go to break the vacuum, you can't flow it through. So all you're doing is putting it in and you're just letting it sit. And then you have to let it come back out, exit through that same hole. So it's not as helpful as doing a nitrogen purge in between your vacuum, your first vacuum, your second vacuum. You're not doing a purge. So that's really nice. If you're doing a triple evacuation, pull it down below, say 200 microns or whatever, and then you break the vacuum with nitrogen. And then after that, maybe let it flow. Let it flow for 5 minutes at a very low amount. So that's a thing. Now, I agree. If you can pull it down below, say 200 microns, and then valve it off with your vacuum gauge, and you're still holding below 200 microns, you know, per the manufacturer's, you know, specifications, then that's fine, you know. But like you said, you have to have heat like as you're removing heat from the system during a vacuum, you have to have heat being replaced. So the line set or the evaporator coil, it has to be able to absorb heat from its surroundings so that any water that's in the inside doesn't freeze on the inside. So valid points, especially if it's during the wintertime. So you could have a residential system in the wintertime, maybe 20 degrees outside. That is, you might want to consider doing that triple evacuation then, because you may have frozen water in their system. It's just really not likely on most scenarios, or even if it is 20 degrees outside, the indoor building a lot of times is still at 60, 70 degrees. And you have that big evaporator coil. You could take the door off of the indoor coil. It's going to absorb all of that heat. Another thing that I like to do when pulling a vacuum and also during the recovery process is to pull the outdoor disconnect on a split system, but let the indoor fan run. So you're providing heat across that indoor coil.
Yes.
And so, it's really not likely. A lot of times you can get by with the single evacuation. It's just some circumstances you just want to be careful. And so, yeah, I think the manufacturers are just trying to stay safe with the language in there.
Absolutely.
Yeah. Cool. So here is a question by a technician named Vince, and he says, why can I not get the saturated temperature to rise when adding more refrigerant to an air conditioner?
Well, if it's not going up, the first I'm looking for is airflow. That saturated temperature is going to respond directly to the airflow. Remember, removing heat from the air. So if I don't have enough heat or enough, aka air, going across that evaporator coil, then I don't have enough heat to absorb. So then I have less heat going across the evaporator. So my pressure is going to drop and my saturation temperature is going to drop also. So you can add refrigerant all day long, but if you don't have enough airflow going through there, you're not going to see that suction temperature rise. And especially if it's frozen up. If you have any ice in that system at all, anywhere, it's going to be exactly whatever refrigerant it is, you convert 32 to that pressure. And that's what pressure you're going to have on the suction line. So airflow is absolutely critical. And then the second thing I look for is going to be a refrigerant restriction. Do I have a clogged up filter dryer? Is there a screen clogged up? Is there a kink in the line, that we're not getting more refrigerant to it? So that's also what's important. I mean, I definitely want to see that saturated temperature. I want to make sure it's above 32 so it's not freezing. But also I want to look at superheat and subcooling. If you look at superheat, I know that I have a superheated vapor coming out of that evaporator coil. Regardless of my pressures, I know that I have a superheated vapor. Remember, a compressor, it can only breathe, just like us, we'll breathe the vapor. It can only breathe the vapor. If you try to let that compressor breathe a liquid, a saturated mixture, then it's not going to last very long. Just like I don't want to be breathing any kind of a liquid. I want to be breathing a vapor. So if the saturated temperatures, I'm glad you're looking at saturated temperatures, but if we think a little bit beyond that of thinking, hey, airflow first, ABC's airflow before charging, and then we're looking at that superheat, that gives us a little bit bigger picture to look at. But first, airflow. I think airflow is the most overlooked part of air conditioning.
Yeah. You hit 2 points. The liquid line restriction, well, you hit a lot of points. But the airflow, yeah, check that first. That's oftentimes what somebody is finding as the final problem. It's like, oh man, you could have just checked that in the beginning. But measuring airflow, it can be difficult in some circumstances. You want to have multiple methods to measure airflow ahead of time. You could use total external static pressure and with static pressure tips. And you can basically compare that to the manufacturer's literature for that static pressure to determine the airflow. You could use a temp rise formula. You could use the true flow grid from TEC, a hot wire anemometer, a rotating anemometer, but then you have to have a certain open surface area where you have to know a certain value based on a grill. So there's a lot of different things that you can do to measure airflow ahead of time. It's just time. And a lot of times, unfortunately, technicians are skipping that and then just kind of feeling at the registers, and that's no good. Most systems are either leaking air or are not set at the proper airflow rate. And a TXV can adjust a little bit, if the airflow is off, but it's not going to be able to maintain, and then a piston is a fixed orifice. There is no maintaining anything. So if you have a lack of airflow and the piston is sized for a 2-ton system and the outdoor unit's a 2-ton, it's going to be allowing that certain amount of refrigerant into that indoor coil. And you need a heat load in order to then have superheat, a saturated temperature above 32 degrees. Another thing that technicians bring up is, what temperature should it be when we're checking the refrigerant charge? Because they find that the saturated temperature falls really quickly down below 32 degrees. And so a lot of technicians are forced to have to check the refrigerant charge, see preventative maintenances when it's not warm enough yet. And so that's another problem there, where you kind of have to wait until you have the indoor heat load at a high enough amount in order to check the refrigerant charge.
Yeah, there's nothing like checking it on a normal operating day. Now there's things we can do. We can heat the house up, turn the furnace on, heat the house up, add a load in there, put blankets on the outside of the condensing unit to try to raise the pressure. But these are still going to be simulations. We can get an idea on it, but with even if you heat the house up manually, it's because there's no heat load outside, you can very quickly cool the house off. So you got to be super quick on it. And I know this is one of the things we have to do. You know, we can't control the weather. We got to do this maintenance check. So we really do the best that we possibly can. You know, you want to tell the boss, no, I got to come back on a warm day. And the boss like, okay, well, you're not going to be paid until it's warm. You know, so there's a lot of variables in there. And just unfortunately, sometimes we can only work with what we have. So ideally, yes, we'd go on a warm day. But little things like heating the house up, using a blanket, and being very quick about it, we can get an idea, but it's just not going to be as good as a warm day.
This is another question that technicians seem to ask, and a lot of times it pops up on the YouTube videos and things, and it's, why is the saturated temperature not rising while they're adding refrigerant? Like, it's holding steady or even going down. And so I remind the technicians, I say, hey, look, as the air conditioning system is running, you're removing heat from the inside of the building, and therefore the saturated temperature inside the building is lowering. And so anytime you add refrigerant, hey, you're adding it, and it might rise, especially on systems that have a fixed orifice. Anytime you add refrigerant, typically the indoor, the low side pressure is going to rise. But with a TXV, the TXV is holding the amount of refrigerant crossing the indoor coil steady, so that saturated temperature won't rise very much, like when you're adding refrigerant. But when you are charging a system and you're waiting in between each time that you're adding a little bit of refrigerant, your heat load in the inside of the building is lessening, the humidity is lessening, and therefore the saturated temperature is lowering. And so I think new technicians just don't seem to realize that, and they're a little confused.
Yeah, so it's called evaporator design temperature. It's typically, now there are a lot of other factors in, but typically your evaporator or your saturated temperature is about 35 degrees below your air temperature. Yeah. So as your air temperature is dropping, your saturated temperature is going to drop as well. And so that's just what we look at. It's great, though, that people are thinking about that and asking these questions. That means they're thinking of that deeper level. So that's good. But we just know as that indoor air drops, so is our suction pressure and saturated temperature.
Yeah. And like you said before, superheat subcooling.
Yes.
Superheat subcooling.
That's the way.
Airflow, and then you need to wait, say 5 minutes maybe before checking the charge with a TXV system, maybe 10 minutes, even longer with a system that has a fixed orifice. So really it's like 10 minutes for the TXV, 15 minutes with a fixed orifice, but a lot of times we're cutting it shorter, 5 minutes and 10 minutes, something like that. So you have to check the airflow first, and even when you're checking your airflow, you can do that with the outdoor disconnect off, but then you're working with a dry coil. So you're going to have more airflow with a dry coil than you will when the system's running with a wet coil. So because you have a static pressure drop across the coil with a wet coil, that's going to be a larger amount than with a dry coil. So yeah, there's going to be less airflow across the coil when it's wet. But anyway, so check the airflow, then make sure during the first maybe 2, 3, 4 minutes of runtime, after about 4 minutes, your saturated temperature should have risen up above 32 degrees. It should be climbing. It should be at about, say, anywhere between, say, 32, 50 degrees is a saturated temperature. That's a wide range. That's not one of those rules of thumb. I'm just saying that's normally where it's at, but it all has to do with the indoor wet bulb temperature. And then after your time increment, then you can go ahead and check with your superheat and subcooling. And so you can kind of figure things out there. A technician by the name of John asks, what does it mean when the delta T is very low, but the refrigerant charge seems to be correct, such as the superheat and subcooling being correct? So delta T very low. So that means that basically you have too much airflow crossing the indoor coil, most likely. So once again, you should be checking airflow before measuring the refrigerant charge. So you're going to measure the airflow. You're going to make sure the saturated temperature is above 32 degrees for that specific refrigerant. And then after waiting, say, 5 minutes for a system that has a thermostatic expansion valve. You can check your subcooling on your high side gauge and your temperature on your small liquid line. If the system is a fixed orifice, then such as capillary tubing or a piston, after say 10 minutes, you can check your pressure on your low side gauge, check your superheat. But the issue is right there with your delta T. So say you have 70 degrees as the return air, and then you only have, say, 65 degrees coming out, but your superheat and subcooling is correct. That means that you're pushing way too much airflow across that coil, and it's not able to remove humidity out of the air because the temperature of the coil is not low enough. And so that's a pretty big deal. So we need to set the airflow correctly before measuring the refrigerant charge. So I would imagine a scenario like that would be if somebody had an oversized furnace or something like that, and then maybe they had one system for the house, and then all of a sudden they're putting a second system upstairs, and then they leave the existing furnace maybe on the first floor, and then they're adding just a half of the load. Like say if it's like a 120,000 BTU furnace, and they put in a 2-ton coil, the blower motor is going to be sized for a much larger amount of airflow to cross that coil, and so they never set it low enough for that 2-ton or 2.5-ton system, and now you just have a system that has crazy high airflow.
Next question should be, what about where your delta T should be at? Like, a lot of people think that it's this magical 20 that doesn't change.
Right.
And we have to understand that system capacity is going to change. So you said airflow, and I agree with everything that you said on that. But also with the humidity in the house, if your humidity level is higher or lower, that's going to affect what your delta T is going to do. And also the capacity of the system. As the outdoor temperature goes higher and your indoor temperature goes lower, your compressor is actually losing some capacity. So there's our conditions where your delta T can be as low as 12 and still be operating properly. If you have a humid house and it's cool inside the house and your outdoor temperature is very high, the compression ratio of the compressor is working really hard and your system simply loses some capacity. So there's actually a method for finding out what your delta T should be generally on a set of conditions. And you can actually exactly find out what your delta T should be in the system performance chart. So you can pull up a chart that comes with that equipment, and you can give in all the information on that chart, and it will tell you exactly what your delta T should be under a set of conditions. Now, it goes a little bit more beyond what we do, but there are some simpler methods of finding what that delta T should be. But it's a little bit more than just simply this, 20 degree, like a lot of people say. So yes, I agree with everything. Airflow is a big one, but also the temperature inside and outside and the humidity, all that affects what that delta T is and should be.
Yeah, I remember even being a new technician in the field and installing a system. I was real new to everything, and it was a fixed orifice system that I was installing. So we're going back, 20 years ago. And so I remember measuring the delta T, and it was like 13 degrees. And I got concerned. And I'm thinking, the refrigerant charge must be off. But I knew to set the system with a target superheat and measure total superheat outside and set the system accordingly. But I got worried because the delta T was lower than what I was expecting. And I remember the senior techs telling me everything should just be 18 degrees. And so with a TXV, a lot of times you may have something close to 18 to 21 degrees as a delta T, meaning the temperature drop from the return air minus the supply air. That's what we're talking about, the delta T. And it's simply not true. It has to do with the wet bulb temperature inside, the outdoor temperature, and it's all going to affect what the delta T is going to end up being that day.
So the HVAC school has an app, and in an app under tools, they have a superheat and delta T calculator. And you enter in what the condenser temperature is, return air, wet bulb is, and the return air dry bulb, and it will actually calculate about your delta T for you. So without having to worry about formulas or charts or anything else, it's a nice, simple, quick little way if somebody's looking for an easy way to do it. I use that because dyslexia, I get the numbers wrong sometimes, but it's a nice, quick little way to do that.
Awesome. Yeah, so check that out over at the HVAC School app.
Yep.
Well, that's a good point to stop today. And it was really great to have you on and to just go back and forth with you. I value you, your friendship, your mentorship, all of that type of stuff has been a huge value to me. And I love discussing these things with you.
Well, I always appreciate our time together. What I really like about this is we can help other people.
Yeah.
I know when I was in the field, there's only a few people that I could ask questions to, and the fact that people can ask the questions, get some help in there, and nobody knows it all. So being able to ask these questions, come in, I think that's important for us to be able to help the people. And that's why we're such good friends. It came together because we're out helping people, helping you. If you have questions, send it out. Let us know. We can't get to every single question, but never stop learning. Keep asking questions. Keep that curiosity up.
So make sure you check out my friend Ty Brandeman over on Instagram, YouTube, TikTok, LinkedIn. He loves to answer your questions, and he's an awesome guy. So I hope you enjoyed this episode. And if you want to learn more about HVAC, make sure to also head over to our website over at acservicetech.com, where we've got a bunch of free resources for you to check out there. And hope you enjoyed yourself, and we'll see you next time at AC Service Tech Channel.